some researchers discovered a 3 billion light year across structure. They call it an arc. I don't know why they call it. I mean, that's fine, I guess, to call it an arc. But that means that there's a new objects. See, cosmology, modern cosmology they don't view anything as an object unless it's a galaxy or maybe a cluster of galaxies. Modern cosmology is absurd. Now, these are just my opinions. I'm a nobody. I'm not an expert in this field. I have researched one individual topic for 10 years. I would never even consider myself an expert in that. But I don't really know that much about astronomy or cosmology when compared to people that are actually working in the field. But they have this narrow view of it also. So there's something to gain from an outside perspective when studying a topic within any of these complex academic areas. And so an outside perspective allows you to view things differently, of course. And so something like this arc that they just, I don't know where you can find this article. I think it's Science News. I clipped the URL out, but just Google arc 3 billion light years. This is kind of recent, but this is just one of many new things that has happened. And it's what it means is this, okay? The universe is infinite and static. It's not expanding. And it's going to be very difficult for cosmology to come to terms with this. There's going to be lots of gnashing and clawing and screaming and wrenching and every other word that you can come up with. They're not going to give it up because they have developed this really complex geometry that's, turns out it's not necessary. You can just go back to Einstein's original general relativity with no cosmological constant, and I'm going to show you how you can do that actually. So let's go to the next slide. These are the main points of the whole thing that I would like to propose. Like I say, I'm not an expert in the field, but I should be able to convince almost anyone the progression through here. These are all each one of these bullet points is all a symptom of the same phenomena or same misunderstanding, the same misconception. And the idea is that gravity is a relative phenomenon. This should be kind of natural to understand. Like, gravity affects all mass. And so it depends on where you're located, in regards to other mass. So it's a relative phenomenon. That's very important to understand. Objects do not possess independent existence. Now, topology and cosmology and differential geometry, all these areas will pretend that objects possess independent existence, and that's just so they can perform the calculations. And that leads to some confusion. There's also the human element to believe that, objects, like we look at the sun and Earth and all the other planets, Jupiter and Saturn. You look at all these bodies as independent things, but they're not. They're all part of a system. They're all connected together. It's all and cosmology has problems with viewing galaxies as independent objects, and that's because they believe that gravity stops at some point. This is literally the truth. Like lambda cosmology, Big Bang cosmology, believes that gravity does not affect things at a certain distance. And that's bananas. That's absolutely bananas. There is zero evidence to suggest that. And so if you can just take that leap, which is natural to me, like I didn't even know this. I had to study like some advanced level cosmology to actually find this out. Like, this is not common knowledge. This is it's just a weird little area. It's almost like they would rather not talk about it. I don't quite get it. But there is no such thing as independent existence. Space is not empty. Okay, they like to pretend, and like I don't want to talk bad about them because I don't really know what I'm talking about. It's just an argument that I'm presenting because this is something that I in my brain I have a fundamental disagreement just from using logic and reason and the first principles. Okay, like instead of justifying the fundamentals from the Hubble redshift, which is what they're doing. I mean, the Hubble redshift is the primary evidence for expansion, and so they're using that. Even though that is an anomaly, let's not think about that yet. Let's get the fundamentals of the geometry down first. Then you can start, tinkering with the theories. You don't use the theoretical to define the fundamentals, and that's especially when it's theoretical, and there's no backing. Like there's a handful of other supporting evidences that's claimed to be supporting evidence of Big Bang cosmology, but most of those things are not that great of evidence. And I'm gonna walk you through all of it. But it's just important for you to understand the fundamental nature of reality, that space is not empty. And I can prove this because look around. It's not empty. And you can say, well, there's some parts that are not empty. Okay, what parts are not empty? Like, you might be able to find a vacuum that's very tiny. Like, you might be able to suck out 100% of the particles in a small region. Maybe. You might be able to do that. Or some very, very, very distant place. But it's still going to have gravity. That region is going to have gravity from the closest mass. And I believe that gravity goes forever. And so, theoretically, you would have zero region that is asymptotically flat. Now, asymptotically flat just means approaching zero. Doesn't necessarily mean zero or completely flat. But it's what is used to justify certain leaps in cosmology, especially in geometrical cosmology. This thing is a mathematical entity. In our universe, you basically have mass and space, but mass is omnipresent. It is everywhere. Okay, like it is everywhere. And when I say that space is not empty, it's literally not empty. Like, the Earth isn't the ground below you, and then there's nothing else. There's an atmosphere. Well, how far does that atmosphere go? Well, I mean, there's some researchers that suggest the atmosphere stretches all the way to the moon because they found oxygen particles on the moon. Maybe not oxygen. They found particles from Earth on the moon. So, I mean, that's not very surprising. I would imagine that over the years, maybe in the future, it will strip away enough to have its own atmosphere. Because I would think that, obviously some particles are going to escape Earth's gravity. And if you look just a random region between Earth and the sun, there's going to be little particles. There's gas, there's particles of mass. But regardless, that doesn't even matter because there's gravitational energy. So, which means that there is no such thing as asymptotically flat space. Now, it's not really even important. It's just this view of the universe that cosmologists have. The perspective is wrong. They're coming at it from the wrong angle, and that is important because that makes them underestimate gravitational redshift. And that's really that's the key to it. Everything in the universe is part of the whole. So you can divide any segment of the universe and call it an object, basically. And it's all, just because you draw a sphere around a region and call it an object, it doesn't necessarily mean it's an object. but it may do so. Anyways, even it is an object. The point is that objects don't stop existing after galaxies. There are stars in galaxies, and galaxies, there's clusters of galaxies, there's superclusters of galaxies, there's mega superclusters of galaxies, there's veins and filaments, arcs apparently. The universe is this giant megastructure in itself, and so there is gravitational redshift. Now, the gravitational redshift is because mass is distributed everywhere. It's like, you just look at the universe as a solid object. The amount of gravitational redshift is going to be directly proportional to the distance of light travel. And so I'm going to show you how to do this. It's very, very super simple. This is all very simple stuff. It's basically, you look at the universe as a solid object. And so the redshift isn't going to be infinite. It's going to depend on the distance, the amount of mass that's in the region of the entire length of the light wave. Does that make sense? Now, this means that the entire universe is gravitationally coherent. And what I mean by that is just everything's connected. It's a chain of connections. So one galaxy has gravitational pull to other galaxies, and the other galaxies have gravitational pull to other galaxies, and it's just like that all across the entire universe. And so you have these giant megastructures, like I say, like the whole thing is a megastructure. It's all connected. Like, I mean, this seems obvious. Like, what is going on? Like, why is some hillbilly in northern Georgia having to make YouTube videos? Like, I'm forced to make YouTube videos because I try to talk to people, and they're like, on forums, they ban you. If you write papers, you're immediately rejected. You have to write to some quack journal. Like, I mean, maybe not, but I haven't found a journal that anybody would even have that would have readers. I got banned from a mailing list because of this. They said no, they didn't want to discuss this, and I'm like, this is very super simple. And if I'm wrong, I'm wrong. Like, but I'm telling you, this is very basic, easy to understand. I can go through this it'd probably take me an hour, but I'm on a roll already, so let's do this. Like I say, large-scale gravitational redshift has been underestimated. Now, I can perfectly align this with the Hubble shift. You can get the 71 kilometers per second per megaparsec. You just using the amount of mass between the observer and the emission. I mean, this is like, I don't know what. Like, is that real? Yes, that's real. I'll walk you through this. So what's the next slide? Oh, my computer jacked me up right there. All right, so gravitational boundaries are arbitrary. That's a very important point. Just because you call the sun doesn't mean the gravity stops at the surface of the sun. Once you zoom out far enough, the sun becomes part of the galaxy. You zoom out a little farther, and the sun becomes, or the galaxy becomes part of the cluster of galaxies. Zoom out a little farther, guess what? There's another structure that develops, and a little farther, and there's another structure. This is common sense. I don't know what else to say. Next slide, please. Here we go. This is what the universe looks like on the largest scale. Like I say, just view it as a solid object and you'll be fine, because guess what? Those pockets that look like there's holes, that's not real. There's gas there. There's gases and dust, and there's stuff, gravity. There's all kinds of stuff in those holes. So it's a solid object. So when light's traveling across, the gravity is emitted from a location that is much more dense than where we're observing it. We're on the Earth. There's not that much gravity here on Earth compared to the stars and everything that you're looking at. Like, all of the things that you would be measuring, the light that you're measuring in this picture would be coming from very massive objects, much more massive than where we're at. So it's definitely a redshift. There's definitely a gravitational redshift. How much is there? Well, modern cosmology says you use the surface of the star, and maybe if you're lucky, they'll use the galaxy. And maybe if you're real lucky and you got some smarties, they'll use the cluster. That's because they're zooming in with this telescope, and all they see is the cluster. Go away, kitty. My cat is annoying. Here we go. Next slide, please. So here's an article from Vice. This is I applaud this girl, Becky Ferrier. I'm sorry, I can't pronounce that, but Becky Ferreira. I don't know. She looks like an awesome, beautiful lady, but she wrote the greatest article I've read on the internet. There's growing it, not really, but it's like the most. To me, this is great, especially even though Vice is probably one of the worst organizations in the United States, it's still mainstream, and so it gives her credibility. I have no idea why anyone would say this, because in my opinion, she's not radical enough. We are way past this. The universe is connected by giant structures. Wow. Why is this news? But I applaud her, because this is the problem in cosmology. Look, and I'm telling you, the entire reason is to fit in the paradigm, to maintain the Big Bang Theory. You don't want to discredit all of science. Well, guess what, dummies? You already have. You've taught. I'm sorry about that word. I may cut that out. Anyways, it's just depressing. It's just depressing because it never should have been this way. It never should have been this way. I wish Einstein hadn't had so much pressure from other people. I wish he'd had time to work on the cosmological constant without a bunch of other people guessing. Here's another one by the same wonderful person. Scientists discovered a gigantic structure in a hidden zone of space. So guess what? This is it, folks. Modern cosmology has been discredited. The universe is not expanding. What else do you need? These structures, according to well, I don't want to get into that. I don't know. This is just an ugly picture I drew of the universe, just showing you that it's a solid object. I don't know why that's still there. These are some of the major players that developed. Now, the guy on the left, the baldy on the left, is Alfred North Whitehead. He is my favorite philosopher of all time. I love this guy. He was a fairly prolific writer. He was a student of Bertrand Russell, and they worked a lot together. And basically, cosmology took a different turn, science took a different turn, physics and math even took a different turn, and they ignored the two greatest minds of the 20th century. And Einstein was wonderful, but all the praise went to Einstein, and all of cosmology developed from Einstein's work. And it's a very shame, because now we're going to have we've got a lot of catching up to do. And unfortunately, we're in an arms race with artificial intelligence. And we already have governments that are basically artificial intelligence, and corporations that are basically artificial intelligence. And they're all very dangerous, and so I don't know if we're going to make it. And it could have been different. If Einstein hadn't have existed, things might have been different. You could go back in time and kill Einstein, and I think that we would all be. No, I'm just kidding. I don't know. I'm just saying that it seems like, and I actually love Einstein. His cosmology was wonderful, especially at first. He didn't like, expansion. That was weird to him. He eventually conceded, but I think it was the 1930s. It took him a long time. So the guy next to Einstein is Edwin Hubble. No, is that? No, Edwin Hubble's the next guy, the guy with the pipe. The guy next to Einstein is Willem de Sitter. And Willem de Sitter is the evil villain in this scenario because he's the one that introduced these quacky ideas about expanding space and metrics that move without gravity. It's a shame. It's like it's was a long, dirty road, and all the academics need to go hop in the shower and come clean of this and start building something new, because the quicker we get started, the better off it'll be. And guess what? It's going to be much funner than the Big Bang Theory. The Big Bang Theory is boring, very boring, and doesn't provide any answers. And I think that there's room for cosmology to provide deep philosophical meaning to our life, and instead it has absolutely whatever. Let's just go to the next slide. Anomalies in the Big Bang Theory. Now this is this is whatever you need it to be. The first bullet point, I'm just going to read through these. See, some of these slides, it's been a while since I've made, and I'm like, okay, I don't know what I was supposed to say to this, but I'm just rambling on, and it's working so far, so I'm not going to stop. The early universe is difficult to explain under the lambda paradigm. Oh, yeah, great point. Great point, Chris. Guess what? Inflation? Whatever. Okay, fine. You have an inflationary period where all mass is expanding around. That's great. Okay, I'm cool with that. Let's explore that for a minute. This would mean that gravity over time would slow things down. Okay? But guess what? Dark energy says the universe is accelerating. So what? I mean, that's just the opposite of what was expected. So what do we have more evidence for? Inflation or dark energy? Oh, we have more evidence for dark energy. At least acceleration, or at least an accelerating redshift. And so what evidence do we have for inflation? None. Absolutely none. None. Zero. Inflation is just an idea. It's how the mass overcome gravity in the beginning of the universe. Doesn't make sense. Makes zero sense. There are structures in the universe that are older than the proposed age of the universe. This is true. There is a star in our galaxy, Methuselah. It's in our galaxy. It is older than the universe. How does that work? What? What? Okay, the universe is not expanding. I'm telling you. Lambda CDM, that just stands for lambda cold dark matter, and lambda means, if you don't know what that just means the expanding paradigm. Lambda is what was represented as the cosmological constant, and so the cosmological constant is the thing that counteracts gravity, but it's just this unknown force. And the cosmological constant isn't really, it's more of a mathematical entity. So to talk about it as counteracting gravity is not necessarily accurate either. But anyways, lambda cosmology and cold dark matter, that just means it's dominated by cold dark matter, but it also includes dark energy in this set, because it's just the mainstream ideas of modern cosmology. And anything outside this paradigm is completely ignored. Like, you have to fall within this paradigm. But that paradigm cannot explain why galaxies have flat rotational curves. That's dark matter. It has no idea. It's a complete mystery. They say that it's dark matter. What? 60%. It would be 60% of the matter in the universe. It may even be more than that, but that's just a guess. I think that's what it would be. Just a ginormous amount. It would take a ginormous amount of dark mass. Like, what does that mean? Neutrinos? Because you do realize how many neutrinos there would be? There would be a lot of neutrinos. Because they don't weigh hardly anything. So what is it? No, it's not neutrinos. Guess what it is? Guess what it is? You've underestimated gravity. Bam! Like, it's just the simplest thing ever. It's the simplest thing ever. There is also mass. There's a lot more mass than people think in the darker regions. Like, it's just dust. Like, there's a lot there. Especially because there's, on the scale that you're talking about, and like I said earlier, acceleration is the opposite of what was expected. Next slide. That's a blank slide. How embarrassing. Alright, this is the gravitational redshift equation. This is just a basic equation off of, I think I got that off Wikipedia, but I mean, it's just, this is how you would determine your the amount of change in frequency. And so the top set, the 1 minus 2gm divided by c squared r, that is, g is the gravitational constant, m is the mass, c is the speed of light, and the r is the radius of the receiver. And the bottom is the source. And by receiver, that just means the observer, and the source just means the whatever is emitting the light wave. So the star. And now, already you can see that there's a problem. Like I said earlier, stars are in galaxies. So, do you count the galaxy? Well, yeah. You can just replace the star with the parameters of the star with the parameters of the galaxy. Okay? Now, what about the cluster of galaxies? Yeah, sure. We can just replace the cluster of the galaxies with, we replace the galaxy with, replace the parameters of the galaxy with the parameters of the cluster, and each scale up whatever structure we're looking at. So how far is this thing? That's basically what you're asking. How far away is this thing? And so the r becomes the distance, which means this, because the bottom gets, the source gets has more and more mass, and the radius gets larger. It makes the receiver, it dwarfs it. So we can just ignore Earth. And so, like, I put this here to imagine, if you don't believe me about the mass in between the place of emission and the observer, between the source and observer, then just consider Saturn. The rings of Saturn affect the gravitational redshift of light coming from the surface of Saturn. I mean, I feel like that's there's an obvious answer to that, and that is yes, of course. The rings of Saturn have a fairly significant amount of mass. It increases the mass, and so you could just, even though the light is emitted on the surface, you could approximate. It wouldn't be exact, but you could just use the radius of the entire area. And so there's also, it really depends on the observer's location, right? It must, because if the observer is on the inside of the rings, then the rings are going to, the role the rings play are going to be different than what it would be if you were outside the rings. Okay? Does that make sense? Same with, a galaxy and clusters and just the whole shebang. Here I have the representation of the equation I just showed you with the radius drawn, A to B. Now we add a bunch more objects. Just add a whole bunch more pieces of mass everywhere. How do you do it? Well, you can, now like I say, this is kind of an approximation, but it works definitely well enough for cosmology. So you include the distance of light travel. That's the only way to include all of the mass. So you would see this radius A to B that you would have here, the M for the mass M1. Hopefully you can see the M1. Wonder if you can, right here. Here is the M1, and this would be the distance between the source and the receiver. And so there would actually be a sphere. I wonder if I have a sphere in the next one. Yeah, I do. You would have a region of influence, and that would depend on the observer's location. Here I have astronauts placed at different distances from the source, and you can see this sphere of influence, or whatever you want to call it. It's just this region between, and so that's the amount of mass. And so that the equation above will be, I'll show you that, how it's shortened here in a second, but I wanted to show you how you can just use density that way, and we can use a density that's scalable. That way that we can use a simple equation for the whole thing. So is what you can do is you just convert mass to density, which gives you the rho 4/3 pi r cubed on the top times the gravitational constant divided by r squared. And so that'll just reduce to gravitational constant times rho 4/3 pi r. Rho just represents, rho's that p thing. It just represents density, mass density. And so now we have this great little formula. There should be a negative sign on that, by the way. Well, I mean, I guess it doesn't really matter. It depends on the perspective. But there's, the perspective we're trying to think about, there should be a negative sign there. Because G is uniform. Now, in the universe that I'm proposing, the gravitational acceleration is uniform. And what I mean by that is that density is inversely proportional to the radius that you're discussing. So in this scenario, well, no, let's just move on for now. There's the sun. I don't know why that's there. There's that again. Here's a good chart. This just shows you that the mass density is inversely proportional to the radius that you choose. So back in this, if you just choose a random region, the size of the sphere that you choose depends on the density will be different on small scales versus large scales. Does that make sense? It's very super simple. Density is inversely proportional to the radius of the region. And that is because gravitational acceleration is uniform in the universe. And that's because there is this kind of an equilibrium on large scales. It's the cosmological principle in a different understanding of the distribution of mass. And everyone should agree that the density of a region, if I just draw a circle here and I draw a little bitty tiny circle here, the smaller circle will have a higher density. The larger circle or sphere will have a lower density. Density is inversely proportional to the radius. And that's because on large scales, the larger the scale, so you know how you have asymptotically flat? It's not. It's asymptotically uniform gravitational acceleration. And it's actually, I don't know what it's approaching, but it's something like 7 times 10 to the negative 10 meters per second squared. You can get to that with very basic equations. So like I said earlier, you can, with the other equation, you can just drop you can just get rid of most of the other part. It doesn't really change the outcome that much. So it's basically an easier approximation, and it makes it easier to keep track of. And you just know that it's a redshift because light is coming from a distant star. The star is more massive than the Earth, and so that's when you have a redshift. You can implement whatever. You can start with whatever density you want. Just pick a density for the scale. You can start with a galaxy, but you really need to be above the galaxy region for this to work. But you can, like I say, if you start at the is what I did. I used 2 times 10 to the negative 26 kilograms per meters cubed for the density at the observable radius. Okay, that's where I started. And then on the galaxy level, it's significantly, it's orders of magnitude greater than that. And so depending on the distance from the source, the light will be redshifted according to this equation, which ends up being this negative GR. That's just, G is just the gravitational acceleration. So, which for, like I say, at the observable radius, 2 times 10 to the negative 26 kilograms per meters cubed, something like that. And I don't know, 4200 megaparsecs, 4150 maybe, 4150 megaparsecs at that radius. Now these, like I say, I'm just throwing it out there. These are kind of some estimates, but at that radius, you would have approximately 7 times 10 to the negative 10 meters per second squared. And that would give you around 74 kilometers per second per megaparsec, which perfectly aligns with Hubble's law. Okay, so you don't just work backwards from Hubble's law. You can use fundamental parameters. Like I say, you can use critical density, which is what I did at critical density estimates. I mean, I think that's a reasonable choice for the density at the observable radius. And so long as you just maintain a uniform gravitational acceleration, so whatever your gravitational acceleration is at the observable radius, there would be that would remain uniform, and that just happens to be that 7 times 10 to the negative 10 meters per second squared. Now, this is not an inhomogeneous universe. This is the universe that we have, so it's not something that's impossible. It's not homogeneous either, because the universe is not homogeneous, and this is obvious because look around. A homogeneous thing would look the same everywhere. The universe is not homogeneous because it does not look the same everywhere. Now, it is very similar, but like I say, it's the density. That doesn't mean the density is homogeneous throughout the universe, and that's what cosmologists believe. That's true. Cosmologists think the universe, the density is uniform throughout the universe. It's homogeneous, and that's not true. Density is inversely proportional to the chosen radius. Whatever radius you choose, density depends on that. Because that's how things work. It's a very simple thing. Now, Lemaitre-Tolman-Bondi cosmology, if that's how you say that. Anyways, this is some people call it an inhomogeneous cosmology. It's not inhomogeneous. It's exactly what I just told you. It can be used for inversely proportional density. My point here isn't to really, I shouldn't have even created this slide. This is maybe a little confusing to some people, but my only point here is that there's ways of dealing with no expansion, and it doesn't. This type of cosmology is a snapshot of the universe, and what I mean by that is that I really don't want to get into that. Everything that I'm saying is super simple. There's no reason to go down these dark roads. But experts should know this, and experts should agree with everything that I've said so far. I may not be perfectly accurate, but what I'm telling you is that you can use gravitational redshift to perfectly align with Hubble's law using fundamental principles. Like, these are first principles, very fundamental stuff. So here I just show you more. This is, I don't know why I wrote this out. Here, Google it. Just Google it. G times, this is just this equation right here, okay? This is the gravitational redshift equation, Okay, so I'm going to convert that to a Googleable formula. Let's go back one. So here we go. And I use this 2 times 10 to the negative 26 kilograms per meters cubed because that is critical density estimate, approximately. And what critical density is whether or not, what if it's, that means that if it's, the universe is more massive than that, then it collapses on itself or slows down. If it's less massive than that, and it continues expanding forever. I mean, that's kind of the idea. It's like the tipping point, the density tipping point. Okay, and so, that's about what you would want to use for the observable radius. And so 4150 megaparsecs is what I'm saying is the observable radius. That's when Hubble's law surpasses the speed of light. Again, all of this is just fundamental guesstimates, but there you go. What else are you supposed to do? I'm guessing here for the observable. So by observable radius, I mean a star that is 4150 megaparsecs away. That star's light will never reach us. Why? Because the speed of light. Because the gravitational redshift, or the gravitational potential, exceeds the speed of light, which means the gravitational redshift flattens out the light so much that you won't be able to see it. It's no longer visible. So that's what I mean by that. This is the speed of light, 300 million meters per second. So that, there you go. You just take the gravitational acceleration, multiply it by the radius, and that's pretty basic there. And here I'm converting it to Hubble's law. So 1 megaparsec is the radius of the region. So if you look at this and you say 1 megaparsec, like you're looking at this galaxy here, and it's 1 megaparsec away, then it's going to look like it's moving away from you at 74, almost 74 kilometers per second. So you would think, oh, that thing's moving away from us at 74 kilometers per second, which is crazy. That's crazy fast, man. I wonder why it's moving away from us. Gravity should be pulling it towards us. Why is it moving away from us? The space must be expanding. Space is expanding. Oh my goodness. Oh my goodness. That means things must have inflated from nothing. No. Stop. It's gravitational redshift. Okay? Now, let's go over collapse time. Now, this is a little gray area, but I'm just doing basic back of the envelope calculations. This is all I'm capable of. Like differential geometry, I would never even attempt to try to do a video on that. So, this is as simple as I can get. So I have the collapse time. This is the amount of time that it would take for a sphere to collapse in on itself, the mass inside of it. So this is just a very simple equation. I think this means for a completely homogeneous thing, but we don't even, it's just like I say, back of the envelope. So here I have this little equivalence. This just comes from the gravity equation I showed you earlier. The gravitational acceleration divided by 4/3 r equals the gravitational constant times density times pi. Now I know that's not very elegant, but it comes straight from the gravity equation. Whoops. And that just allows me to replace this 2 pi, or not 2 pi, but the it just allows me to work with it. And so you can see my transformation, and we just eliminate the we don't really eliminate, we combine these, And so we end up with this equation, which, so here's what we're talking about. So this is the universe. You have that collapse time. The collapse time becomes directly proportional to the radius. That's the point. The point is to show you that if this ball is bigger, then the collapse time takes longer. And so that just is what that means is that, you know, depends, at some point the universe is so big that the collapse time is never going to happen. And it just keeps going like that. Okay, now that's just a guess from me. That's how you deal with the collapsing universe. Cosmic microwave background radiation, CMBR. So this is a map of the CMBR. This is supposedly evidence of the early universe. I don't know what that means. It's light waves that was given off from the mass that was in the early universe. Whatever. That makes... okay, whatever. It was hot. But gravity didn't pull it together yet. And space was expanding. Inflating even. And so it's supposedly something like 2.3 degrees Kelvin. The average temperature of that. And this would be the isotropies. If I don't know if that's a word or not. These would be, you know, these anisotropies. That is a word, not isotropies. Anisotropies. This is the areas that, you know, it's different in some areas. You know, it's not perfect. There's slight deviations. I'm going to explain to you what this is. The cosmic microwave background radiation. Remember how we was talking about critical density and all this, and at the observable radius? Well, okay, if there's stars at the observable radius and it's gravitationally redshift so much that you can't see it, it's kind of like a black hole, right? And so this is the temperature equation for the Unruh effect and the temperature equation for Hawking radiation. These are extremely similar ideas, okay? So the Unruh effect is very similar to Hawking radiation. Hawking radiation just means that a black hole will give off some radiation. We'll be able to escape it, and that's how you would determine the temperature of it, that equation. And the Unruh effect is basically the same thing, except for it's if you are in an accelerated reference frame. So if you are accelerating, or if you are standing on a gravitational body, if you are in an accelerated reference frame, you will see acceleration where there is none. So, and by where there is none, I mean where an observer that's at rest will see none. So if you're on Earth and you look in some area, you'll be like, oh, there's no radiation there, so I can't determine the temperature of it. Bummer. Then you start accelerating, you're like, oh wow, I see radiation everywhere. I can measure it. The faster you go, or the faster you accelerate, the greater the redshift. Whatever. Hawking radiation. You can use these equations. You can use either one. You can say it's going to be the same thing. I mean, you just want to use the gravitational acceleration. Do I not have another slide for this? I thought that I had a whole Google thing worked out. Maybe we'll just cover that in another video. Is there any questions? Now is the time to ask. I may never make another video. I absolutely hate making these videos. I don't like this burden of having to explain cosmology to everyone. I would rather not deal with this, but no one else is talking about it. No one else is talking about it, and I just don't understand. I don't get it. This seems really basic. Like I say, 10 years ago, I was just interested. I was like, so why do they think that the universe is expanding? And I really got to looking into it and found out about Hubble's law, and I'm like, whoa, that's weird. I was like, I bet there might be another way of explaining that redshift. And then I was like, you know what? And just a few weeks before that, I had learned about special relativity and redshifting light and general relativity. And so I was just like, you know what? I bet it's one of those. I bet it's gravitational redshift. And then I was like, let me just check it. And then so I did. I was like, how do you determine the gravitational redshift of a star that's way over there? And I was like, oh, you can just use the distance and the average density. And so I did, and I was like, whoa, that actually works out. And then it took me forever to figure out why this wasn't the way to do it. This is not the way mainstream cosmology does it, but it should be. So, in other words, once again, let's say you're right here on Earth. Let's say the Milky Way galaxy is right here on this side, and there's a star right here in a galaxy. Like, you can zoom into this, and these are just galaxies. These are strings of galaxies and filaments and veins and whatever. But it's all a bunch of stars. So we're right here on Earth, and there's a star over here. So the star emits light and comes over here. You have to look at the light wave as a single object. And what I mean by single object is it's a light wave that has X amount of crests and X amount of waves. And the distance between that star and the point of observation and the mass that's in the sphere that's surrounding this, okay? Like you can use that as a radius and draw a sphere, and that encompasses all of the mass that should be playing a role. May not be perfectly accurate, but it's going to be good enough for cosmology. And so when you do this, the amount of redshift matches up with Hubble's law when you use the fundamental parameters like the I'm getting tired. The cosmological, the density, what is it, density? Critical density. Good grief. Thank you. Whew. Brain, work. Okay, good night.